Hello, and thank you for turning into this virtual presentation. My name is Gabriel Plummer from the Mechanical Engineering Department and the Materials Science program. I'm going to be talking today about kinking and layered crystalline solids, which is a unique and potentially useful deformation mechanism. So kinking is a deformation mechanism unique to layered materials, and these are materials with strong in-plane bonds and weaker out-of-plane bonds. The prototypical example of this is graphite. Kinking occurs when compressive strain is applied parallel to the layers. At first appearance, there is no clear mechanism for plastic deformation in this configuration, as there's no resolved shear stress to cause the layers to slide past one another. The only option would seem to be layer fracture. But what we observe is a buckling of the layers to accommodate compression, thereby converting expensive in-plane strain to cheaper out-of-plane strain. Rather than a continuous elastic buckle, however, a distinctive kink band forms bounded by two sharp kink boundaries. Kinking is observed in a wide range of both natural and engineered layered materials at numerous length scales. These include geologic formations at the kilometer scale, laminated composites at the millimeter and micron scale, and then layered crystalline solids going all the way down to the atomic scale. The focus of this presentation will be on the atomic scale kinking mechanisms in layered crystalline solids, although we can certainly draw some similarities to other materials and systems. So now shifting our focus into layered crystalline solids, I want to start with a brief history of developments in its study to give context to our new results. The very first published observation of kinking in layered crystalline solids occurred in 1898, more than 100 years ago, when it was documented in a number of naturally occurring minerals. Moving forward to the 1940s, Orawan observed kinking in single crystals of HCP metals loaded parallel to their basal planes. He declared that this was an entirely new type of plastic deformation when dislocation glide was inhibited. Soon thereafter, however, Hess and Barrett repeated some of Orawan's experiments and asserted that kinking could indeed arise from a combination of elastic buckling and subsequent nucleation of dislocation dipoles, which would then glide apart to form the kink band and its associated kink boundaries. Frank and Stroh developed this idea in some more detail, determining quantitative criteria for which a kink band would form and become stable. And I like to consider this the classical kinking theory. And despite a lack of direct evidence, it has been largely accepted for the past 70 years. A major reason for this is a lack of work on the subject thereafter, and this is because kinking only occurs in HCP metals under very specific loading conditions and is not very relevant to their overall plasticity. However, beginning in the 1990s, the development of max phases has renewed interest in kinking. Max phases are ternary carbides and nitrides with an inherently layered crystalline structure. They comprise a large family of materials and have attracted a lot of interest due to their combination of both ceramic and metallic properties. Due to their highly anisotropic bonding, max phases deform readily by kinking, unlike HCP metals, and it's been linked with some of their unique mechanical properties. I'll briefly touch on perhaps the most intriguing max phase property associated with kinking, and this is their ability to dissipate large amounts of mechanical energy. When compressed or indented up to gigapascal stresses, they form fully reversible hysteresis loops. Combined with their high stiffness, this is a very unusual combination indeed, as most engineering ceramics typically only possess the high stiffness. So it's our hope that a better understanding of the kinking mechanism should allow us to take advantage of this unique max phase behavior, among others as well. So now let's move into some multiscale observations of kinking and max phases, which have only recently been enabled by new single crystal synthesis techniques. First, here are in situ SEM images of a max phase being indented, which show its high propensity for kinking. If we look at some of the more magnified images on the right, we see that in addition to the kink boundaries marked with dotted lines, some of the layers appear to just be elastically buckled with that continuous curvature. This indicates that there is indeed a very close connection between elastic buckling and kinking, as classical kinking theory would suggest. Secondly, here are atomic scale high-resolution TEM images of a max phase after being indented, and they reveal a delamination crack beneath the indenter and strikingly a kink band that is only 3 unit cells thick. This provides clear evidence that kinking is governed by atomic scale mechanisms. So now that we've seen a few experimental examples, I'll get into the atomic scale simulations that we've used to take a closer look at the underlying mechanisms behind kinking. The natural starting point was to simply replicate the in situ indentation experiments, and these results give us quite a bit of insight into the nuances of kinking. The simulated microstructures are strikingly similar to experiments, with numerous delamination cracks and kink boundaries. Now, however, we can take a very close look at the steps which occur to produce this kinked microstructure. We see that when the layers beneath the indenter initially bend, a band of slip is nucleated, and slip calculations reveal that oppositely signed dislocation walls do indeed make up the kink band and its associated kink boundaries. The delamination cracks allow for many additional layer bending modes and the resulting complex kinked microstructure. Taking a close look at the numerous kink boundaries reveals that most of the layers simply bend as we see in the SEM image, but there are a few which have fractured as well, which look a little bit more like the high-res TEM image. The close connection between elastic layer buckling and kinking becomes completely clear when looking at atomically resolved snapshots of another simulation showing the nucleation and growth of a single kink band. Initially, the elastically buckled layers create a non-zero resolved shear stress on the basal planes. You can note the slight offset from the vertical in the leftmost image there. The resolved shear stress quickly becomes large enough to nucleate dislocation dipoles, which then glide apart forming the kink boundaries. These are indicated by the Berger circuits in yellow and blue, depicting oppositely signed dislocations. Additionally, the red-colored atoms show a column of atoms initially with zero dysregistry, which then develop increasing dysregistry as the dislocation dipoles nucleate. This process repeats itself inside the kink band, nucleating additional dislocation dipoles and thus increasing the kinking angle and relieving more in-plane strain. The results we see here are the first dynamic demonstration of this mechanism and largely confirm the core ideas of classical kinking theory from 70+ years ago. There are, however, some important differences to note. The kink boundaries we see here are not atomically sharp, as has been typically assumed, but exhibit a pronounced curvature of the basal planes over several nanometers. The layers have only deformed elastically, as indicated by the closure of Berger circuits drawn even at extreme kinking angles. As such, we expect these boundaries store large amounts of elastic strain energy, making them reversible so long as they don't become pinned by lattice resistance to dislocation glide. This creates quite a compelling explanation for the extraordinary mechanical damping properties displayed by max phases, with these tightly coiled layers almost acting as mini springs. We also note that these curved boundaries tend to delaminate in regions of maximum curvature and can transform to something closer to classical kink boundaries when the basal planes do finally fracture. These key differences have prompted us to start referring to these boundaries as replication boundaries to distinguish them from the classical kink boundaries. And this is inspired by the idea of replications or atomic scale ripples, which have been observed in the basal planes of van der Waals solids such as graphite. So in agreement with the observations made here, recent high-res TEM images in layered crystalline solids, including max phases and graphite, do indeed indicate that the boundaries typically assumed to be atomically sharp classical kink boundaries at lower resolutions, as seen in the upper pane, are in fact likely replication boundaries with curvature of the basal planes spread over several nanometers, as shown in the lower pane. We suspect additional work on other layered crystalline solids will serve to further confirm this idea. So now to wrap up, I'd like to present a few summary points. Kinking is ubiquitous in layered crystalline solids and is driven by the need to redistribute strain from energetically expensive in-plane bonds to cheaper out-of-plane bonds. The underlying mechanism couples atomic layer buckling with the nucleation of dislocation dipoles. It's important to note that these cannot be separated. The latter cannot occur without the former. Unlike the kink boundaries described in classical kinking theory, the replication boundaries in layered crystalline solids are curved at the atomic scale and thus highly elastically strain. Finally, the work done here should serve as a foundation for better understanding kinking and max phases, and by extension other layered crystalline solids, thus enabling us to better leverage some of their unique mechanical properties. And finally, we'd just like to acknowledge some of the funding sources for this project. The Corstec Company, Army Research Office, National Science Foundation, as well as our experimental collaborators, both in the US and in Europe. Thank you for taking the time to listen to this presentation.